Good morning, everybody. This is exciting. There's a bunch of you here, and so we're going to be doing some fun math things today with R. And so you'll be able to actually run R code and write R code. If you've never used R before, that's okay. We're going to spend a little bit of time getting you up to speed with kind of the basic R commands that you'll need to know to be able to make these cool maps. And that's kind of the main point for today, is to be able to take raw geographic data that you find out in the world and then do cool stuff with it and make pretty maps that tell truthful stories. And so that's kind of the goal for the next few hours here. And it should be fun and exciting. So before we officially get started, if you want to run this R code along with me and then do the different exercises and stuff that we'll be doing, you don't need to install anything on your computer. If you go to the website that I just put in the chat here, rstudio.cloud, if you already have an account there, neat. If you don't, make an account really quick. I think you can connect it to your Google account. So if you're already logged into Gmail in your browser, you can just click on one button and you'll create an account, and it should be fairly quick. So go ahead and make an rstudio.cloud account. And then one more URL that I'm going to stick in the chat here. All of the materials for this workshop, all of the slides and all of the code that you'll be running and a whole bunch of other useful resources are all available at this website here. This andhs.co/GPL-GIS for Georgia Policy Labs. GIS, and we'll be talking a lot about GIS today. That stands for Geographic Information Systems. It's a fancy acronym that just means like geographic data. That's all it means. So if you click on that link, it'll take you to a little web that has everything that you'll need for today. So go ahead and do that. Let me share my screen here so you can see what's going on. Okay, so this is the little website that you should be able to have access to now with all of the materials for today. If you want to make sure that the RStudio Cloud account that you just made is working, if you notice in the materials section, there's a link that says all the materials for today's workshop are accessible in this rstudio.cloud workspace. So go ahead and click on that link, and it should open in your browser an instance of RStudio, which is where you'll be able to run R directly in your browser. You don't have to install anything on your computer, and it should just work. So go ahead and get that working, make sure that that's fine. If you have R on your computer and you're familiar with RStudio, that's great. I actually have a zip file here on the workshop website here. And you can just download that and open it on your computer and run R and RStudio locally rather than in your browser. So while you're doing that, let me introduce what we're going to be doing today. So let me pull up these slides here. Okay. So I'm really excited to be here today. I am not a geographer. There are official people who get PhDs in geography, and they spend all their time kind of making maps and doing geographic calculations, and that's their thing. What I do, as Tyler mentioned, I study nonprofits and regulations of nonprofits around the world, especially how dictatorships try to kick out nonprofit organizations and NGOs. And so lots of the GIS stuff that I do is just making maps and showing locations of NGOs around the world, highlighting different countries that have passed specific laws. And that's generally my world of GIS stuff here. It's not super complicated. I'm not calculating like distance and like grand circle routes for airplanes to travel or anything like wild like that. It's just basic map making. But even then, I found that it's a really important skill to be able to take map data out in the world and do stuff with it. And it's something that lots of programs don't really have the ability to do. Excel, one of the most recent versions of Excel, has a way to do maps but it has to connect to some external resource, and it doesn't work super well. Other programs like Tableau make it okay to make maps, but it's kind of a tricky thing to do. And so the goal for today is to have you be able to take data that you find on the internet or internally in your organizations and stick it on a map, and be able to show off kind of different trends that you can see geographically. So that's what we're hoping to do today, or what I'm hoping to do today. But what I want to know really quick, in the next couple minutes, is go ahead and use the chat window and answer these two questions, because there's like a couple dozen of you here, and you're interested in this GIS stuff. And so I want to know why you want to figure this stuff out, and when do you ever use maps or GIS related things in your job? So go ahead and in the chat, go ahead and answer those questions really quick, just so we can get a feel for why you're here. Maps are very engaging. People love maps. Everybody loves a good map. And like, some of my earliest memories are like sitting in like my parents' living room when I was like 5 and just looking through atlases and memorizing maps, because maps are super cool. And I think lots of people have similar feelings about maps. They just look neat. And so we can do this. Also, for data analysis, maps and knowing how to do this GIS stuff is really, really important, because you often have to to specific regions and districts. This happens all the time with like voting districts and finding where voters live in specific geographic zones. Katie in the chat here mentioned matching student addresses for charter school students to attendance zone boundaries. So what you have to be able to do for that to work is somehow have geographic information for each student, and then somehow create like geographic buckets and count how many people are in each of these buckets on a map, which is kind of tricky. It's a whole another dimension of working with data. And so it can be hard. But fortunately, we have lots of tools that make all of this easy, making the maps, making accurate maps, and doing all of this geographic calculation stuff. So it should be fun and exciting. Cool. So plan for today is we're going to start off talking about kind of the philosophy behind presenting geographic data and why it is so hard, and why most programs like Excel don't really try to do maps, because it's way easier to just make a scatter plot. It's just points with an x-axis and a y-axis. And those like axes are easy. But with geographic data, axes are not easy, because we live on a big like round globe thing instead of a flat map. And so you can distort all sorts of things just based on the X and the Y axis, which makes visualizing this stuff really, really tricky. And so we'll talk about how you can tell truthful stories using maps, and how you can different ways of showing data on maps. Then we'll take a little bit just to give a really brief overview of how R and RStudio work, the basics of a plotting graphics package called ggplot, and then the basics of a data manipulation package in R called dplyr. I think it stands for like data plier, like the tool plier. It lets you manipulate data. I think that's the pun they're going for there. So we'll do that, and again, we'll be able to do all of this in rstudio.cloud. If you haven't made the account at rstudio.cloud, go ahead and do that. Then this is the bulk of the session here, is showing you how to make these maps and do some fun GIS related things in R using a package called SF, which stands for Simple Features, which is some geographic computer sciencey term for geographic data. I don't know why they chose to name it that. They just did. And that's what it's called out in the world, is this SF package. So again, all of the materials for today and everything you'll need to be working with is at this website here, and hs.co/gpl-gas. So again, if you haven't gone there to start getting the materials ready, go ahead and do that. So let's go ahead and start talking about maps and why they are so hard. I've been mentioning like the axes get distorted, all sorts of other things get distorted. So let's show um, kind of the power of maps and the pitfalls of maps. Okay, so maps, as we mentioned, are a really powerful tool for trying to understand data. They're very compelling things. Everybody loves maps. They go viral on social media all the time, whether or not they're true, just because we like looking at maps for whatever human evolutionary reason. Maps are cool. So one of the first times that maps actually made a difference in public policy and public health specifically was back in the mid 1800s in London. There was a huge cholera epidemic in Soho, one of the regions of London, where 10% of the population in Soho died within a week, which is super dramatic. We've seen already with like COVID for the past 15 months, we've seen rapid rises in infection rates and death rates, and it's been miserable. But we have not lost 10% of our population. Over the course of a year and a half. These guys lost 10% of their population in a week. So it was a huge public health disaster, public health emergency. And nobody really knew what to do about it because germ theory hadn't been invented yet. And so, according to doctors at the time, the way you fix cholera is you change your air and breathe better air because the disease is in the air. It was a thing called miasma theory, where miasmas were like these bad vibes and bad spirits in the air that made you sick. And so, according to miasma theory, everybody should have left the area and gotten better by breathing beach air or something. The hard part about that, though, is Soho at the time was a very poor neighborhood, a very working class neighborhood. And so you couldn't really just uproot thousands of people and take them to the beach for 2 months so they could relax and start breathing better air. And so everybody was dying because they were stuck in this bad air. So what this John Snow did, he was an early epidemiologist, is he decided to map out all of the cases of cholera and all of the deaths that came because of cholera to see if he could find any patterns. And this is what he did. This is his famous Broad Street map. So on this map right here, if you look carefully, there's a whole bunch of lines. It's basically like a bar chart on streets is what he did here. So you can see Broad Street right here is this road right here in the middle of the map. Um, it was right outside of a workhouse, which was kind of like an orphanage for adults. It was just like a homeless shelter type place where people worked for very, very, very low wages. It was an awful place, which again, like you couldn't move everybody from the poorhouse out to the beach to breathe better air. And right outside of the poorhouse is where you see lots and lots of cholera cases. You can see this bar. It's really, really long because this is where most people were getting sick. There were people down the streets that were also getting sick, but everything was clustered around Broad Street right here. Nobody was really getting sick in these other streets and these other blocks in Soho. And what John Snow discovered is there was actually a water pump right on the corner of this Broad Street and this other street here that was right outside of this huge bar of everybody dying from cholera. And so he went out to this Broad Street pump. It's still there today. It's a monument now because of its public health implications, and discovered that the water that was coming out of here was somehow infested with cholera. It wasn't because of miasma, it wasn't because of bad air, it was because of bad water. And so, what he recommended to city officials was to shut down that pump, and people stopped dying of cholera pretty quick. And so, they were able to sanitize the water system, and it started to revolutionize public health. Queen Victoria took this up. Florence Nightingale took this up and helped revolutionize kind of sanitation practices in the British military, and it became a thing after this, in part because of a map. Where John Snow was able to see the patterns in this map and be able to identify the source of the contamination and the sickness, and it fixed all sorts of things. And so, because of this map, they were able to uncover kind of a deeper truth out in the world and improve people's lives. which is the ultimate goal of any map you should ever make, is change the world, I guess. So maps are cool because of that, but maps are also dangerous because we, for whatever reason, inherently trust them. And so they can be used to tell untruths. For instance, you see stuff like this all the time on social media. People love to share maps because it looks like there's obvious trends here. And so if you look at this, this is back from 2017. I've had lots of relatives sharing this map where it tries to draw a direct correlation between the 2016 presidential election results and crime. And so look, it looks like a perfect match there, which sure, there's a whole host of reasons why that might be the case. If this is an accurate map, it's because like most Democrats live in cities and most crime occurs in cities, but the correlation is not causation story here. Like just because Democrats live in cities doesn't mean it's causing crime rates. And so there's that story. But the really interesting thing about this is that bottom map, the government released crime map of 2013, is not actually crime. Those are the results of the 2012 election. So really it's comparing the 2012 to the 2016 election, which if you know anything about presidential politics, generally if a district or a state votes for a president in one election, it's probably going to vote for the same president in the next election, just because of how demographic trends work. Except in the case of Georgia this year that flipped. But like, again, that's like a total lie right here. This comes up all the time. This is another one. They actually used a crime rate map instead of a fake map of like election results. But again, it's that same story of like crime happens where people live. That's why crime happens, not because of Democrats. But these things go viral and get shared millions of times because it's a map. Um, there are dangers with this in the whole world of fake news, where there's these content farms in like Eastern Europe that are writing fake news stories. Um, Lots of them have discovered that maps go really viral, and so it's easy to make fake maps and have that go viral. One instance of this, which you'll always see, you see maps like this all the time, where it says America's favorite candy, America's favorite food, the best or the most preferred sports teams per state, the most interesting Google results or Google searches across states. You've seen maps like this all the time. This looks authoritative, I guess, but also it's just like it doesn't say where this data came from, and it kind of just distorts weird trends. Is it true that the favorite candy of Montana is beef jerky? That's weird. Um, Guessing that the most popular candy across the whole country is something like Snickers, because that's like the Coke of candy, I guess. It's just everywhere. According to this, the most popular candy in Georgia, which you can probably all not confirm, is the Haribo peaches. Peach, I guess, gummy peach things. I've never actually seen these in the wild, but it's here on the map, so it must be true. Um, which again is just bizarre. So whenever you see something like this, you can pretty much just discount it, which is great because inherently you're supposed to be discounting these dumb maps. But we like maps. Maps are supposed to tell us truth. We want the Jon Snow type maps, which makes it really hard to distinguish between good maps and bad maps. Even if you're trying to do something official and try to be very careful about how you present the geographic data, you can still run into other pitfalls. For instance, this comic here, you'll see this all the time. This is also related to the crime rate map, is that basically anytime you try to show any sort of national trends, like this panel here says our website's users, subscribers to Martha Stewart living, they're the same map. And this map down here, they're all basically the same. And it's because most of these maps that show the density of things getting used are just population maps. And we see that even with simple things like if you want to draw a map of all the public schools in Georgia, you'll get a whole bunch of dots, and we'll do this later in the session where we'll actually make a map of all public schools. And you'll try to start drawing policy implications from it, but really it's just a population map. Schools appear where people are. And so it looks super official, but all you're seeing is just population density, which isn't necessarily helpful. Sometimes you can have helpful maps. One commonly abused type of map is called this choropleth map, where instead of putting dots on a map, you shade different regions of it. And so this choropleth maps are helpful. There's this cool website called the Fall Foliage Prediction Map. You can go to it later this year, and it shows you different regions of the country and when the leaf colors will be the best and prettiest. And so you can kind of see different regions across the country. That's good and helpful. But choropleths can also distort truth and distort actual underlying trends. Maps for elections are probably the greatest offender here. And often you'll see, again, going back to the election map, people will often claim that America is a deep red country because look how red it is. And so conservative policies must be taken seriously 100% of the time, discount all of those tiny blue counties because it's a majority red country. This map right here, the 2016 results, was hung in the West Wing during the Trump administration. And it looks like it was an overwhelming landslide for Trump. But the issue with this choropleth is that it's coloring each of these counties as 100% red or not. And so when you're in like the West in Wyoming, where like 6 people live, it looks super dark red. But the issue there is that land doesn't actually vote. The people on the land vote. And so if you have a map like this is the 2016 election results, watch what happens if we resize each of these election districts and congressional districts into regions based on population. So if we click on this, that's the election result map there. The issue here is this looks like a map. You can like navigate with this map. If you look at this though, people see this and they get kind of like, that looks weird. That doesn't look like a map. You can't plan kind of a cross-country road trip using a map like this. That's just a whole bunch of blobs. And so lots of people don't like maps like this. These are called cartograms. But it does represent the underlying data in a different way, where it shows that it's not really that the whole Western United States is super deep red. It's Western United States is mostly empty with lots and lots of red dots. It's definitely Republican over here. But again, this shows where the people live. And you can see giant clusters. Here's Georgia right there. Atlanta's a very split region right here. And so this is potentially a better way of visualizing this instead of just results using a choropleth map. Cartograms, here's some other versions of it. Again, this is the choropleth version. You can put these in different bins. These are little hexagons that I think the New York Times does this sometimes, which again, this is kind of unnerving because that doesn't look like a map at all. That just looks weird. But it does help show like the different congressional districts, like each of those are districts instead of counties, which don't correspond to districts. This is the best one. That just looks ugly. It's kind of a map, but it's again trying to show these trends in election patterns. This is from the 2015 UK election. They have the same issues. Pretty much any democracy will have these same issues of representing election results on a map. This is the choropleth version here. It looks like the country is deep conservative. This is all just blue. And there's one little red spot here where the Labour Party won in 2015. So it looks like Labour is not very widespread. But Labour is, or this little spot here is London, where like millions and millions of people live. And so if you do this goofy version here, there's London and it's a lot bigger. And all of these emptier areas get shrunk down. Or if you do it by, they don't call it congressional districts. I think they call them parliamentary constituencies. So each of these hexagons is a constituency. And so it shows, again, kind of better balance in the map than just this choropleth here. One other attempt at this is this comic here. This is the same idea, showing that land doesn't vote. Each of these stick figures is 250,000 voters for either Trump or Clinton or other. The only other on here, I think, is in Utah there. That's Evan McMullen from 2016. But this, again, shows kind of it's not a deeply red country. It's not a deeply blue country. Pretty much every state is very split. Like if you look at Montana, which is red in all of the other maps, it's really kind of just evenly split between these two people there, the 500,000 people that live in Montana. Wyoming has just one person there. Dakota is just one person, which again is a different way of looking at this, rather than just kind of displaying the data as a choropleth and just filling huge swaths of the country with solid colors, which isn't super accurate. So those are a whole bunch of different reasons why maps can distort truth and how they can distort truth. Another way they can do it is just because of the physics of maps. And it's related to this idea here. Here's a ball. If I was super brave, I would like cut it open, but I don't want to like cut myself. The issue with balls, pretend this is the world. If you want to make a map of the entire world, you basically cut this globe open and then spread it out. It is not going to go flat because of how balls work. If you imagine like cutting this ball in half and then I stick this half sphere on a table and then squish it down, the center might be nice and flat, but then the edges are going to curl up. And so then to make it flat, I have to like cut the edges so it goes flat, but then that starts spreading out the shapes that go on the edges of wherever I'm trying to center the focus of the map here. And there's no good way to transform this ball into something that's perfectly flat and perfectly representative of the ball. And so the way you do that is through something called projections, map projections, which are different ways of basically cutting up a ball and showing it on a piece of paper. And so there's a whole bunch of different ways to cut up a ball. There's no one way to flatten this thing. You can cut different regions to highlight specific areas of the globe that you want to show. And so let me show you some different things. If we click on this link here, it's also, if you go to this website with the all of the resources, it should have a section on projections where you can see these different things too. So if we scroll down here, here's a bunch of different ways of looking at the world and cutting up this globe and flattening it. And if you notice, they're all different and they all resize continents in different ways. So pay attention to Africa and Greenland as this is happening, because Africa is right in the middle. And so if you're trying to flatten a globe, you're going to focus maybe on the equator. So but then Greenland is way up near the North Pole, and so that's going to get distorted more. So watch this map and see how big Africa and Greenland are in comparison to each other. And there are some wild differences occasionally. Kind of one of the biggest differences, let's skip to Mercator. Oh, they don't even include it because it's so bad. I'll show that in a minute. So that's close enough. So this is the Miller projection, which I guess is like Mercator. But according to the Miller projection, look at the size of Greenland compared to Africa. It's like the same thing. Because this kind of projection kind of over exaggerates the size of the Northern Hemisphere, which is why imperial and colonial administrations back in like the 1500s and 1600s really liked this projection because it made Europe a lot bigger than Africa and other regions that they were colonizing. So there's a whole bunch of like political stories and political power wrapped up in these projections. But it really does kind of distort our notions of the size of countries. If you click, if you go back to the resources page, there's a link here called the true size of. So if you come here, this is wild to me here. So we're familiar, this is the Mercator projection right here. So notice how Greenland is like massive. It's bigger than Africa. So what this lets you do is you can grab a country, for instance, here's the United States. It's the size of the United States. But if we drag it over to like Europe, for instance, it's bigger than Europe. So like driving from France to Ukraine would be like driving from Kansas to New York City, I guess. That's the kind of the distance within the United States of Europe here. If we move the United States, though, down to Africa, look how much that shrinks. This is just wild to me. So if you move the United States down to like equatorial Africa, um, we can put Seattle kind of where Ghana is. So if you want to drive from Seattle to Florida, that's going to be basically the distance from Ghana to Angola and Zambia, which if you're looking up here doesn't look the same. Like this shrinks down the United States substantially. Um, India too looks like a little country, but if we move India over to the United States, it's basically like one edge. So the western edge of India goes from Nevada to Ohio, and then from the Canadian border down to like central Mexico. China, for instance, let's grab China. China is just as big as the United States here. If we stick China in Canada, they're about the same size. Um, so again, like this, hopefully this is like mind blowing to you. I love this website just because it's so fun. Um, because our notions of how big the world is are completely distorted by our maps. Google Maps, which you probably all use, relies on the Mercator projection. So if you open Google Maps on your phone right now and zoom out, you'll see this exact map, which means your perception of the world is getting distorted funny because of the map world in which you live. Which is great. So maps are hard because of these projection ideas. There's a whole bunch of different ones. We already saw some there. Mercator, this is super common. You've all seen this in elementary school classrooms. This Gall-Peters one looks super goofy. It's super elongated, but it also more accurately represents the sizes of these different areas. One of the best ones for just trying to see the world in general as accurate as possible without overly distorting Greenland and underly distorting Africa is called the Robinson projection. It's similar to what the National Geographic uses for their world maps. They use something called the Winkle triple projection, which is a goofy name, but it's similar to this Robinson one. Even in the United States. So we've been talking about world projections here, but if you're looking at kind of a specific state or a specific country, projections don't matter as much because again, if you think about this ball, if you're trying to show the entire ball on a flat piece of paper, that's going to be hard. If you're just trying to show a chunk of the ball, just the little circle here, you can extract that and that's easier to flatten out and there's going to be less distortion. But even within countries, you can get distortions from projections. So here's two common projections in the United States. This is called NAD 83 because it just is. And this is basically what Google Maps uses, and it works. It's not a bad projection, but if you notice the northern border here, it's completely straight. That is because these follow the latitude and longitude lines on a globe perfectly. And so this is good for like navigation. You just drive straight across the northern border and that's going to be a straight line. But in reality, it is kind of curvy when you think about the ball again. The United States is not like perfectly flat. It does kind of bend around a little bit. And so if you use something called the Albers projection, it resizes these things better. So if you look at like the state of Washington here, it's a little bit smaller than it would be over in this NAD 83, which is, this looks more stretched out and elongated than Washington does here. This is especially the case with like Alaska. You've often seen maps where like Alaska is just down here in the corner. We'll actually make a map like that today. But Alaska it's kind of like Greenland because it's up far north. And so it can be massive or it can be small depending on where it is on the map. So where do you find these projections? Because there's like thousands of them. There's this website here, this epsg.io. This is like the European something with a G for geography. I don't know what it stands for. But it is kind of a main central database of all different projections that you can use. And they are super detailed. You can find kind of a general, like the Albers projection for the whole United States. You can also find projections for specific states. So you can find a projection for Georgia specifically. There's actually like 8 or 9 different Georgia specific projections. There's actually regional projections. You can get one for just Atlanta, just Savannah, because again, basically you're just zooming in on just Savannah on this thing and then flattening it out. And because the world is round, there's still going to be distortions, even if you're just looking at like Rhode Island. They have a couple different projections for like North Rhode Island and South Rhode Island. So these databases here are really useful for finding these projections. This is another one. The workshop website that you have access to, I have some of the more common ones listed there. And so that's kind of a useful place to look for these projections. And here's a couple other resources you can look at to better understand how these projections work. Which one is the best? Which one is the most truthful, accurate? Which one should you always use? None of them. There are no such thing as a good or a bad projection. The question isn't good or bad, it's appropriate or inappropriate. So Mercator is disgusting for like showing the world in total. Like hopefully the main takeaway from today is never stick a Mercator world map in any of your reports ever again. Which is hard because like Excel and Tableau default to Mercator because they do. So it's bad for visualizing stuff, but Mercator is good for like navigation. That's how the GPS systems work. It's the negative 180 to 180 degrees idea with latitude and longitude. That's basically the Mercator projection. So it's still useful. It's just not useful for visualizing stuff and communicating data. So keep that in mind. Hopefully from now on, anytime you see a map, you're going to be thinking, what projection is that? And hopefully I've ruined you that way. So there's a whole bunch of different ways of putting data on these maps, and it gets tricky because of this projection idea. So if you look right here, you can put lines on maps. That's neat. So if you look at this is from the census. You can tell they care about projections. This uses the Albers projection. The telltale sign of that is this curved north border here. It's not straight. Which then means any lines they put here also have to be kind of curved because they're trying to show that most people are moving from like the Northeast, New England to California, and they're not drawing a straight line, they're doing a curvy line. You've probably noticed this also if you've taken like a transatlantic flight ever. If you look at just a globe, it looks like if you're going to fly from like New York to London, you just kind of go straight across. But when you actually fly, you end up like over Greenland. You do this big circle. They call it the Great Circle. And it's because that's the fastest way. And it looks weird, but that's because of projections and weird distortions and how globes work. And so the same thing here. This looks like it's kind of out of the way. You can just go from here straight to California, but this is actually the fastest route. And it's kind of the better way of displaying that data on the map here. So you can put lines on maps. This is a really cool place. There's this live wind map. If you click on this link in the slides, if you're following along, it takes you to a website that shows you what wind trends look like in the United States right now. This is a screenshot I took back in 2012. This is Hurricane Sandy. When it hit New York, you can see huge wind patterns there, but these are really just lines on a map. And that's all. This is a really cool map here. This shows every river, stream, and waterway in the United States using information from the Census Bureau and a bunch of other federal agencies. And again, it's just a map with lines on it, but it represents kind of where all the water is in the United States. And again, you can tell this is Albers because of the curved north border. Sometimes you can rearrange maps to make them to emphasize the data you're trying to show. This shows every hurricane since 1851 up until like 2016, I think is when this person made this, which you can kind of see that it's this swirly whirlpool shaped thing. But if you look carefully, this map here, the center, this is Antarctica. And here is South America. Here is Mexico and the Gulf of Mexico. And I think Florida is like right here somewhere. Here's Baja California there. So you can see that most hurricanes kind of start over here in Africa work their way over to the Gulf of Mexico, and that's kind of where it's getting hit the most. There are some that hit the Pacific side of Mexico. There's some typhoons over here in South Asia. But what these people did, the interesting thing here is they took kind of the standard projection of the world and focused on Australia, or not Australia, Antarctica, which then helps them tell the story better, which is cool. You can also stick points. You've seen stuff like this. This shows vaccination rates for kindergarten students in California. And you can see this is from 2015, 2016, that there were huge clusters in LA where parents weren't getting their kids vaccinated for the measles because of anti-vax sentiment. And so you can visualize big clusters of red zones here. We've gotten really used to maps like this in the past year and a half because of COVID, where we can identify outbreak clusters and how bad the risk is across the United States and across the world. And so we're getting better at this. This map is really interesting. If you don't look at the caption, you can try to guess what city this is based on the points. So the red dots here, this is data from Flickr, which was a photo sharing website back in the early 2010s. It's kind of defunct now. But all the red dots are photos taken by tourists, and all the blue dots are photos taken by residents of this city. And what's really neat is you can actually see the outline of the National Mall. This is Washington, D.C. So here you have the Lincoln Memorial, you have the Washington Monument in the middle here, you have the Supreme Court up here, the White House right here. So this is just kind of central DC where all the tourists are. All of the locals take pictures way out on the outskirts because that's where they live, and they're not kind of taking tours every day and wandering around the mall. And so you can see different trends in a city just because of the points. Couple other final ways of just doing neat things with maps. These are called Voronoi Maps, where they basically say you take this point and you try, like this region here, every point in this region, the closest main point is down here. And so really each of these points here is the capital of states. And so this is imagining if you drew state boundaries so that you were the closest possible, so you live the closest possible point to a state capital. So for instance, here's Montana. According to this, people that live like down here in central Idaho should in theory belong to Montana, because it's closer for them to drive to the capital of Montana than it is to Salt Lake City or Boise. So that's what this is showing here. And so that looks goofy, but it also works if you're doing kind of marketing ideas, trying to figure out market segments for things. This map here shows the closest NBA team for every city or for every region in the United States. And so like up here, the Portland Trail Blazers, in theory, somebody that lives in Montana is closer to the Utah Jazz than to the Trailblazers. If you're down here with the Hawks, for instance, where we are, geographically, it shows that people in South Carolina are closer to the Charlotte Hornets than they are to the Atlanta Hawks. And so that might be kind of geographic reasons why South Carolina roots more for the Hornets than they do for us. But these are also just all Voronoi maps. Couple final examples, you can actually make maps without maps. This right here shows, it's just a whole bunch of rectangles sized by population, indicating some specific policy change from the Affordable Care Act. And so the interesting thing here is that these squares are all positioned like a map. So Florida's down here, Georgia's right there, North Carolina, California's over here. So it's really just like, it's basically a glorified bar chart, but in the shape of a map. But there's no projections or anything here. The map aspect of it just makes it feel more navigable. Instead of looking at a big list of alphabetic states, you can look here and generally know this is the Southeast and this is the Northwest, or yeah, so you can figure that out. Or something like this. There's a whole bunch of lines showing unemployment rates from 2000 to 2016, but it's in the shape of the United States. Sometimes it gets really tricky when states are small. Like if you look here, we have Georgia, with West Virginia right above Georgia, which isn't the case, but that's just how the grid has to work. So it's not always perfect, but it's another way of kind of using the map idea to communicate something about the world. So with that brief introduction to the dangers of using maps and the good things about using maps, we're going to start making some maps using R and RStudio. And you won't be able to make every single one of these maps. You can make lots of these using basic principles that I'll show you using R and RStudio. So to get started, if you look at the workshop website here, go ahead and click on the link for the RStudio.cloud workspace. If you did that already, it may have kicked you out. It times out after like 10 minutes of inactivity. So if you don't have that open anymore, go ahead and open it. And we'll go ahead and do a super brief introduction to R and RStudio if you've never used it, just to give you enough experience and enough knowledge to be able to do cool stuff with it. So go ahead and get that open. And then in the chat, once you have RStudio Cloud open, put a thumbs up or say yes or okay, or give some acknowledgement that you've got RStudio open and ready to go. To get started, I'm just going to do a super brief overview of how RStudio and R works for those of you who haven't used it, in part because we promised in the workshop description when you all signed up for this, that this is designed for people who have never had any experience with R, but also for people who have. So we want to have everybody have the same foundation here. So R is a statistical language, a programming language, just for stats and for making graphs. It's similar to Stata, except R is free, which is great because you don't have to pay hundreds of dollars for Stata or SPSS or SAS or other things like that. One thing that is confusing to people is this difference between R and RStudio. So R itself is a program that sits on your computer and runs calculations. If you've ever used Stata, R is basically just the little console thing where you run commands. That's all it is. There's no fancy windows for it. There's no menus for it. It's just kind of a scripting language. That's all R is. And so if you imagine this analogy of kind of a car engine, that's what R is. It's just the thing that does stuff. RStudio is a program that sits on top of R and kind of makes it easier to use. It provides windows, it has some menus, it shows you plots, it shows you, it lets you edit text and edit scripts, and it makes it a lot easier to use the engine. And so that's, if you think about RStudio as kind of the dashboard for this underlying R engine thing, that's what we're doing. If you install R on your computer, you have to install both parts. You have to install the engine itself, and then you have to download RStudio separately so it can sit on top of the engine and do stuff. So that's the difference between these two here. So a quick tour of RStudio itself. You should all be looking at something like this on your screens right now. So RStudio is neat because like this window right here, this console, this is R itself. That's all R is. It's just a place where you can type stuff and stuff happens. The rest of RStudio, like these different panels and these different panes, are the dashboard. It's the thing that helps you use this console better. So this console area, you can type stuff there, press enter, and stuff will happen. So go ahead and type 2 + 2 in that console and press enter. And then in the chat, tell me what number you get. Yeah, 4. If you didn't get 4, I'd be concerned. So good. That you just ran your first R command if you've never ran R. Yay. So that you just type stuff in there and run it and it shows you stuff. That's how R works. So congratulations, you got 4. You might see this one thing here. The reason that's there, you can ignore that. you can actually chain like multiple commands together. Like you can say 2 + 2 and 3 + 3, or you can do whole vector calculations. You can have a whole list of numbers and add 1 to it. And so then it would say like the first number is this, and the second number is this, and the third number is that. But because this is just one thing that it returned, that's what that 1 stands for, is the first thing that it returned. So the issue with typing stuff directly into the console is you have to retype it. So if you want to rerun this again in the future, you then have to remember I was doing 2 + 2, which again is super simple right here. But if you're making a complicated plot with like 20 lines of code, you don't ever want to retype those 20 lines of code in the console. And so instead, you type it in a document and then run the code from the document. And RStudio makes it really easy to use, and I'll show you how to do that. This area of RStudio is the files pane. It shows all of the files that R has access to, which is great. So go ahead and in there should be a file named 01gettingstarted.rmd. Go ahead and click on that and open it. And you should have it open in kind of the source pane. And it'll change RStudio to look like this. It should shrink your console down a little bit, and it will show this text editor window here. So this is where you type stuff. There are a couple different ways of typing things in R. You can save documents with a .r extension, which is just an R script. Everything in that type of file is just R code. But if you use something called an RMD file, which stands for R Markdown, the neat thing about this is it lets you combine just text. You can type whole reports just with regular language. There's no code involved. And then you can mix code within that text, which is really neat because you can basically have like a notebook for your analysis, where you can combine, you have text that you write, and then you have code, and then you have output. And so you can actually generate whole reports. You can make it so that it hides the code when you generate the report. And so nobody knows that you used R for this. You just click on a button and it'll make a fancy Word file or a PDF or an HTML file of your document here. It's really neat because you can actually have these things update. So if you have like a database that you have to pull from and you're making a new report for the week, you just click on a button, it'll download the latest data, make the newest graphs all automatically, magically. It's great. So R Markdown is neat. So what you're going to do is within that R Markdown document, scroll down to the first code chunk. So code chunks are delineated with these triple backticks, and it'll be a slightly different color on your screen. Up in the top corner of the code chunk, there's a green play button. If you click on that, it will run that chunk. And then you should be able to see a picture below. So go ahead and do that, click on play, and you should get a cool picture. Yeah, if you're doing R and RStudio on your laptop, what you'll need to do is, if you download this zip file that's on the workshop page and unzip it, and then you'll want to open, so the folder will look like this. You'll want to double click on this rproj file here. This is an R project file, and that will open RStudio and point it at this folder. And then you should be able to open this R Markdown file just fine. If that doesn't work, you can go ahead and use RStudio Cloud and do everything there as well. You should see something like this. When you click on this play button, it will run this chunk and you should see a cool picture. Like, come on. Thinking about it. There it is. There's a plot. Okay, so what I want you to do now is scroll down to this next section that says add a new code chunk. And I want you to insert a new R chunk here where you can actually run code and put 2 + 2 in it and run it. So that's your next little job. So add a new chunk, put 2 + 2 in it and run it. Okay, so to do that, I'll delete the text. Again, none of this text here is R code. That's just text. I can write whatever I want here. Boo, boo, boo. So to insert a chunk, if you click on this little green button, you can have it insert an R chunk. The nice thing about this R Markdown thing is it actually works with a lot of languages. There's a way where you can have a Python chunk run Python code maybe scrape some website, collect the data from it, and then you can pass that code to an R chunk. So you can actually do Python and R and SQL all at the same time, which is like super magical. So we're going to insert an R chunk, and then I'll type 2 + 2. And then if I click on the play button, it should run it. And there's 4. Okay. So having everything in the document here is nice, but you can also finalize it by doing something called knitting, where what it'll do is it'll go through each of the chunks in the document, run them, make whatever graph needs to happen, output whatever text needs to happen, and then put it into one final document. Oh yes, Leslie says if you type Control-Alt-I, that will also insert a chunk. That's the easiest way to do it. I don't actually ever click on this green button. If you're on a Mac, you do Command-Option-I, and it'll insert the chunk, which makes it nicer. You can also run a chunk if your cursor's in it, instead of moving over and clicking on the green button. If you press Command-Shift-Enter or Control-Shift-Enter, it will run the whole chunk. If you just press Command-Enter or Control-Enter, it'll run one line, which in this case, there's only one line in the chunk, so you can't really tell that it did much. But let's say 3 + 7. So if I do Control-Enter and then Control-Enter, it'll do line by line. If I do Control-Shift-Enter, it'll do both at the same time, which is neat. Okay, so when you're working on this, if you click on this button up at the top that says knit, what this does is if I click on this arrow, I will knit to HTML. So it will go through the document, run each of the chunks sequentially, and then convert this into an HTML file. It should pop it up here. Voila. Cool. So it ran this library function where it loaded a library of functions. And then here's the plot directly in this HTML file. And here's our 2 + 2 and the 3 + 7 that I added. So it has the code and the output all directly here in the document, which is super neat. This is an HTML version. I could knit to Word. I could knit to PDF if you install a thing called LaTeX or LaTeX, which we won't talk about today. So we'll just be knitting to HTML. But that's kind of the basics of how our Markdown works. And again, the point for today is not to show exactly how that works. The reason we're doing this is because I find that it's the best way to combine our code and text. And so we'll be using it throughout the workshop, where you'll open up a file. I'll have a bunch of code that you can run by clicking on the play button, but then it also has just text explaining what's happening, and then code that you can run, and then text, and then code. And then sometimes it'll say your turn. And so you'll insert a chunk and do stuff with code there. And so it's a convenient way to keep everything in one place. When you knit the thing at the end, you basically have a self-contained collection of notes to yourself for future you, which is fantastic. So that's why we're using this R Markdown stuff. It does make life a lot easier. Couple other final quick things about R here, just basic R. There's 2 lines of code. If you scroll down in the R Markdown file, you'll see them. They do 2 different things. So go ahead and run each of those chunks and see what is different about them. This filter empty cars CYL = 4 versus this one that looks the same but is slightly different. And in the chat, go ahead and tell me what you think is different about them. There they are. So if you scroll down to my line numbers are different because I hit enter a bunch of times. Near line 50-ish, you'll see them. Okay, so this first chunk that just says filter empty cars, it sends the output directly to the console. And so you can see this data here. Actually, if you can minimize this console because it's showing everything directly in the document. So if you click on this little line button here, it'll shrink it down. So now you can see this data set. What it did is it filtered this built-in cars data set and is only showing rows where these cars have 4 cylinders. So that worked. It's directly in here. When you run this next chunk, a couple of you in the chat said nothing's happening. And that's true. You don't see anything, but things are happening. Yes. If you look in the environment panel, this is a super important panel. This is one of the most powerful things about RStudio. It tells you what variables you've made and what data sets you've made. So notice how there's now a thing here called 4 cylinders. If I click on the name 4 cylinders, it will open up a new tab here that shows that same data set. But now I can actually work with this 4 cylinders data set. So if I wanted to plot all of the cars that only had 4 cylinders, I can now use this instead of the full data set. And this keeps a list of everything that you've loaded and all of the different variables you have, which is really helpful. So the way you do that is with this backwards arrow thing. For weird historical reasons, R uses that backwards arrow thing. It's from the days in the 1970s when keyboards actually had a backwards arrow that you could use for assigning variables. It does work if you do equals. It's just the way the R world works is with this backwards arrow because it does. If you don't want to type that backwards arrow, because it does get annoying having to do like 2 keystrokes, like with shift involved, it is super annoying to type manually. If you type option minus or alt minus on Windows, it will insert that arrow for you, which is neat. So that works for anything. So if I said like, if I make a variable called X and then do alt minus 1, and then if I run it, nothing will show up down here, but over in the environment panel, I now have a thing called X, which is 1. So if I run X by itself, it will show up. If I run 4 cylinders by itself, it will show up. So that's how you can see it here in the document. You can also click on it here, and that's great. So that's how you make variables and stuff in R. So the environment panel, again, that's one of the most powerful parts of RStudio. Lots of other R programs don't have this. I rely on this thing all the time. It's great because of this viewer panel. The other cool thing about the viewer panel is it lets you sort things. You can like sort by weight. You just click on weight, or sort by miles per gallon. And you can filter even, I think. Yeah, which we already filtered for that, but we can say, here's just the low displacement cars. So neat stuff with RStudio. Okay, so that's the basic overview of how to use RStudio. So next what we need to do is explain a couple R packages or libraries. So before we explain that, first I need to explain what a package is. So if you've ever used Excel, which I'm assuming you all have, Excel has functions inside it where you, if you want to get like the sum of a bunch of cells, you type equals sum, opening parentheses, and then select your cells, and then it adds them up. Sum is a function, which means you just feed it data, you feed it cells, you feed it something, and it spits out something else. It spits out a number of the total sum. Excel has a bunch of built-in functions like sum and average and stdev for standard deviation, a whole bunch of other things. But what Excel doesn't let you do is if you want to make your own function, if you want to make a super average, average is already in there, but if you want like a fancy version of average, you can't do that. It doesn't really exist. Or if you want a different way of plotting stuff in Excel beyond clicking on menus, you can't do that. R is similar. It has a bunch of built-in functions like mean. Like if we want to get if we say mean of the numbers 1 through 4, that should give us 2.5, which makes sense. That's 1 plus 2 plus 3 plus 4 divided by 4. That's how averages work. So mean is built in there. It just exists as a function. But the neat thing about R is that you can actually write your own functions to do whatever you want. So R has some built-in, like a plot function. So if you say plot 1 through 4, it will make a really ugly plot showing the numbers 1 through 4, both on the x-axis and the y-axis. Neat. So that's the built-in plot function in R. But smart people have made other ways of making plots. something called ggplot, which stands for the Grammar of Graphics plot, which we'll talk about in just a minute. And so ggplot and other kind of custom functions don't live in R by itself. They live in something called a package, where somebody has written a bunch of functions, and then you can download that onto your computer and load that package, and then you have access to all of the functions that other people have written. If you notice at the very top of this getting started document, there's this first line, or line 7, says library tidyverse. That loads a collection of 8 different packages that all kind of work together nicely. ggplot is one of them. And so if you run that, then you have access to some fancy functions that let you do neat stuff. That's basically what it is. For historical reasons, you have to run library tidyverse, even though tidyverse is a package. You don't run package tidyverse or package SF or anything like that. They're kind of interchangeable, this idea of a package versus a library, just because that's how it is. So that's what packages are. Is just other neat ways of doing stuff in R with custom functions. So what we're going to do briefly is talk about kind of the most logical way I've found, and lots of people have found, for visualizing data and thinking about how to visualize data in R. And so we'll do a super brief introduction of this package called ggplot. So first, what do you all think, knowing what you know about cars, is the relationship between how heavy a car is and its mileage? Is it going to get more miles per gallon or fewer miles per gallon? What do you think? Heavier the car, less miles per gallon. Yeah, I think so. I know absolutely nothing about cars, but there's a cars data set built into R that we use all the time. So what I want you to do is go ahead and open the second R Markdown file. I think it's called, if we go to the Files panel, Visualize Data, open that R Markdown file and scroll down to your turn 1. And what you're going to do is run this code and then click on the green button to run it. So you'll want to type this, pay attention to the spelling, capitalization, the number of parentheses, make sure this is accurate. So go ahead and do that. I'll give you a couple minutes. There's a timer, it works. Type that in there and run it and see if your intuition about a negative relationship is true. So you have 1 minute and 48 seconds. All right, time is up. Let's go ahead and run it. So I'm going to type it here. So we're going to say ggplot, that is a function. So we open parentheses, we're going to say data equals mpg, which is this miles per gallon data. So if we run this, you can actually see what's in it. So it has columns for car manufacturer, car model, displacement, which I think is weight, year, cylinders, a whole bunch of other stuff. So we want, so data equals mpg, then we're going to add this plus sign, and we're going to add this weird thing called geom point. And we're going to say mapping equals AES, X equals disple, Y equals HWY, but with an equal sign. So if you run it, you should get a cool picture that looks like that, which is negative. So the heavier the car is, the worse miles per gallon it gets. So you were right in the chat. Good job. So that is how ggplot works. I'll explain what all of that weird syntax means. There is actually a logic behind it. So you should have gotten a picture that looks like this. So what this does, notice how you had to specify a few different things. You had to specify a data set that you're plotting, which, if you come from the world of Stata, is a little bit different. In Stata, you're only ever allowed to have one data set open at a time. And so any plot commands that you run just happen on whatever data set you have open. In R, you can have as many data sets open as you want. So if I look in my environment panel right now, I still have 4 cylinders. I could plot that, but I also have this MPG thing too. I can plot that. I could have like 20,000 different data sets in here and plot all different versions of different ones. So you have to specify the actual data set that you're working with. Then we have this thing called mapping, where we're taking a column in the data set, so displacement, for instance, and mapping it to the x-axis. And we're taking the highway column and mapping it to the y-axis. And then we're showing those two columns as points. So that's what's happening with this ggplot stuff here. And so just to give you a basic overview of what that means here, there's that AES function that you saw stands for aesthetic. So this comes from this idea of this Grammar of Graphics book that was published like 20-ish years ago, where basically what you're doing is you're taking stuff in a data set and you're mapping it to specific elements in a graph, whether it's X and Y, or the color of the points, or the size of the points, or the shape of the points. You could imagine having that car plot that we just made, coloring the points by manufacturer, coloring the points by the number of cylinders they have, having little triangles for manufacturer and colors for cylinders. You can do different columns in the data set and have them show up differently within the picture. So that is basically what you're doing with ggplot, is you're saying take data and map the different columns in the data to different aesthetics in the plot. And so this is the general template, which is what you just typed here. So you said so you have some data set, and then you map the columns to different parts of the graph, and then you show that using some sort of geometric shape. It can be geom point, which is what we just did. You can use geom line, and it'll draw lines between the different mappings you have. You can do box plots, you can do histograms, you can do all sorts of things, but it follows the same template where you say, I want this one column to show up on the x-axis. I want this column to be the size of the points, or the thickness of the line, or the color of the line, or the fill of the columns if you're doing like a bar chart. And so that's basically the template for ggplot. So what I want you to do, so here's a bunch of different aesthetics to show an example here. So you could map one of your columns to color, and it'll color the points by the different values. Or if you do like a continuous column, it'll do kind of a gradient and show the darker, going from dark to light. You can you can have different sizes, you can have different shapes, you can have different transparencies. You can do a whole bunch of different things. And the way this looks in code is this is the same code you just typed, this ggplot, the MPG data. We're going to use points. We're going to put displacement on X, highway on Y, and we'll color it by class, which I don't know what class is. Compact versus SUV versus two-seater, that's what class means. So this would put all of the points in a scatter plot because we have X and Y, but it would color them by class, or it would size them by class, or it would use shapes by class. So you'd get triangles and rectangles and stars and circles. So what I want you to do, so for instance, the color equals class, you can see these different colors, and it adds an automatic legend here. We still have displacement and highway. So what I want you to do is go down to your turn number 2, look at the MPG data set, and start experimenting with it. Stick some of those columns that you see in the MPG data set as different aesthetics. So after you say X equals something, Y equals something, then do comma, size equals cylinders, or shape equals cylinders, or class, or something. Just try mapping some of these different columns to different parts of the graph. So go ahead and do that. I'll give you a couple minutes. I forgot to do the timer here, so I will keep track of the time. And yeah, go ahead and experiment with your turn number 2. You're going to be putting everything, make sure you put it after this Y equals highway. So you're going to say color equals something. And make sure the column name that you type has to match one of the column names in the data set with the same capitalization and everything. So go ahead and play with that for just a minute. Okay, so let's come back. You can see I'll do some stuff here. So let's do color equals drive, for instance, like 4-wheel drive versus rear-wheel drive versus front. So if I run this chunk here, That looks neat. So we have 3 different colors happening, with green for front, blue for rear, and red for 4-wheel drive. So you can actually see that there's some heavier cars over here, this cluster here, that have a higher highway miles per gallon than should be expected here. And they're all rear-wheel drive, which by cars, I guess that's a thing. So we can color by drive, we can color by class. See what that looks like. Aha, so these heavier, higher miles per gallon cars are all 2-seaters, and there's no other 2-seater cars that are over there, so that might explain that difference there. We can do multiple ones. We can say color equals class, shape equals drive, and what this will do is add 2 legends. So now they're shaped like these squares are all rear-wheel drives, but they're also colored at the same time. So you can get lots of different information just kind of stuck in the same graph, which is really, really neat. Because you're just, again, taking columns in a data set and mapping them to specific aesthetics. What we could also do, we can use alpha, for instance, and change the transparency. We'll say alpha equals highway. So what this will do is fade stuff. So the points with higher highway miles per gallon will be less transparent, and the points with lower highway miles per gallon will be more transparent. I don't know why you'd want to do that in real life, but you can, because again, you're just taking columns and mapping them to aesthetics. And that's the whole point of ggplot. That's the grammar of graphics, the interplay between columns, aesthetics, and geoms, which we've been using geom point here. But there are other geoms. So there's like geom call, geom text, geom point, box plot. The thing we're going to be working with in a minute is this geom SF for simple features, which lets you plot maps. And then you can also fill the maps by colors. If you want to fill by population or fill by vote share, you can color them. You can have different borders. You can have different transparencies. You can do all of the same aesthetic things that we've been doing with those points, but 2 pieces of a map. There are tons of different geoms. If you click on this link here to the ggplot documentation, it'll show you all the dozens of different geoms with a whole bunch of different examples of what will happen. So that's a really helpful resource there. So next, if you go down to turn 3, before you actually run it, look at this code and try to guess what's going to happen and then run it. And I have this 2-minute timer, but really it takes like 20 seconds. So go ahead and like look at this, guess what it's going to do just based on your knowledge of ggplot, and then see what happens. So the neat thing about this is it has 2 different layers. It has geom point and it has geom smooth. So what you should get is something that looks like this. And the magic part about this is the only thing that changed was the geom. If you look at the mapping, both of them use displacement on the x-axis and highway on the y-axis. But we could switch between points and this smooth line just by changing the geom, and you can actually overlay them. You can have multiple layers just stacking up on top of each other, which is super helpful because you can make all sorts of complex graphs, which is going to be important when we get to the GIS stuff, because you can have a rivers layer, you can have a cities layer, you can have a lakes layer, you can have a borders layer, and you're just going to overlay those on top of each other, and they can all share the same aesthetics, and it gets fairly simple to make really complex graphs. One other little point here, if you notice this one that you ran, this seems like a lot of extra typing, where we had to say map displacement and highway to X and Y for the points, map displacement and highway to X and Y for the smooth line. And if you add more layers, you're gonna have to keep doing that, and that gets really repetitive. So what you can actually do is if you set any aesthetics up in this initial ggplot function, those all get passed on to any geoms that come after. So here, instead of having to say mapping equals AES, blah, 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 because I set it here, any geom I add after that will also use those same ones, which is helpful. Anything you don't put in there, will only apply to that layer. So right here, this is putting X and Y for all the layers, but then it's only coloring the points. So the points all get colored, but there's a single line. If I put color equals drive up here, what would actually happen is you'd get 3 different lines. You'd get a green line, a red line, and a blue line, because the color aesthetic would get mapped onto the smooth layer 2. So where you put these aesthetics matters. So really quick, just an overview of how this works. This is, again, a super brief introduction to how the philosophy of ggplot. What you're really doing is working with layers after you map specific aesthetics from your data set to parts of the graph. And then you just sequentially add these layers and build up a plot. So here's an example of what this looks like. So here we're starting with a data set, this MPG data, and we're going to map these 3 columns to different parts. So displacement, highway, and drive, which is what we've been working with. Then what we can do is add geom point. Great. There's geom smooth with the 3 separate ones, and it's separate because we're coloring the smooth lines by drive, because it's up here and it's being universal. We can then control the smooth lines. We can tell them to be straight. We can then add another layer to change the coloring system, to use this other palette here called the Viridis palette. We can then separate this into facets. And so here's the 4-wheel drive cars, the front-wheel drive cars, and the rear-wheel drive cars, all in sub-panels here. We can then add another layer to add a bunch of labels. So we have a title and a subtitle and a caption and fancier things. We can add one more layer to change the theme. So we got rid of the gray background. We could change the font. We can do a whole bunch of other stuff. We can then adjust the theme a little bit. So we made the title bold. We moved the legend down to the bottom. And so really, that's kind of the final version. So all we did was sequentially add stuff. So we start with this, and then if we step through it, we're just adding layers to this plot that make it fancier and more polished and refined. So that's kind of the basic way of using ggplot here, is just layering stuff to show the data in your data set. Again, we can't cover everything in like the 20 minutes we spent on this. I have a whole class at GSU dedicated to just ggplot, like a whole semester of just that. So that's great about ggplot here. So you can go ahead and look at those resources, or just Google ggplot and you'll find stuff. So the slides for that, if you go back to the workshop materials, that was 2B, visualize data with ggplot. And if you click on the link there, there's the slides. Fun fact, if you press the letter O on the slides, if you're following along, it'll show you an overview of all the slides. You can scroll through and jump to different sections. So those are the slides. Okay, so that's super quick overview of ggplot. Don't worry if it is too over your head. You'll be able to see it better once we start making the maps and stuff. It will make sense, I promise. So the last little thing we need to talk about is transforming and manipulating data, and filtering data and adding new columns and doing things with data sets in general. So let me grab this over. So you've already seen this idea of the tidyverse. It was a package that you ran in one of the R Markdown files at the beginning. And basically every R Markdown file we're going to work with today uses this tidyverse. And the reason why I like using the tidyverse when teaching, but also in my regular data analysis, like in the actual research I do 100% of my stuff with tidyverse, because it helps with, it's just a neat way of thinking about data and a language for manipulating data and graphing and plotting data. What it does is it makes R feel more like human language rather than machine language. So if you have a language like C++ or Java, it's a really esoteric way of programming. You have to think about like variable types, and you use lots of brackets and curly braces, and it's trickier to use. Base R by itself without any packages works kind of like that. If you want to select like the third column in a data set, and the second row, you have to do like this weird bracket notation with a comma, and like it can get a little bit tricky to work with. Tidyverse sits on top of base R. It's just a whole bunch of functions in R that make it more like English to work with data. You're actually using verbs instead of esoteric shapes on your computer. And so it makes it a lot easier and more intuitive to work with data. It's called the tidyverse because really it's just a whole bunch of packages that work together using this idea called tidy data, which we won't talk about today. That really just means you have a row, like every observation has its own row and columns. That's what tidy data is. These packages all kind of work together nicely. We already looked at ggplot. Their packages. We'll look right now at dplyr that lets you manipulate data. It even has a picture of pliers. tidyr lets you switch data sets from like wide format with columns for years to long format. So there's just like one column for year all the way down. A whole bunch of other packages that just work together nicely. The great thing about dplyr, which is the package we'll talk about right now, is that it is basically English, where you use these functions that are verbs. So you can extract rows from a data set using filter. So you're just filtering the data. You can select specific columns using select. You can arrange the data set and sort it by using this thing called arrange. You can make new columns using a function called mutate. And then this right here, if you've ever used pivot tables in Excel, this is basically pivot tables for R. You can make groups within your data and then summarize. So you can get like group averages or group sums, a whole bunch of other things. We won't talk about that today. What we're going to look at specifically right now because of the GIS stuff is filter and mutate. So filtering is important because that lets you select just specific rows. We already saw this with the first R Markdown file that we used, where we just looked at cars that had 4 cylinders. You can also add new columns in a data set using mutate. So we'll use those two and show how it works. So with filter, you select rows that meet some sort of logical test. And the way you do it is you say filter, take the name of the data set in there, and then you give it the test, which we already saw previously with like filtering the MT cars data set so that cylinders was equal to 4. Here's another example. So this data set here is called Gapminder. It's a whole bunch of countries and years and life expectancies and GDP data, a whole bunch of things like that. So if the data set looks like this, and I run filter the Gapminder data set so that the country is Denmark, you can imagine what that would look like. It will give you a data set that looks like this, just Denmark across all the different years. Great. There's a whole bunch of different ways of doing logical tests in R. You have less than, greater than, equal to. You can have less than or equal to, greater than or equal to, not equal to with this exclamation mark. So that's how you filter. So what you're going to do now is if you open up the third R Markdown file in the RStudio Cloud workspace, you're going to filter some data. So your job in the next couple of minutes is to use filter to show only the data for Canada, all the data for countries in the Oceania continent, which is, it's called continent in the data set, and then rows where life expectancy is greater than 82. So if you come to the third R Markdown file, transform data, go ahead and run the chunk to load this Gapminder data. It's a good idea to like open the data set in this tab and look at it so you can see kind of what it is. And so come down to your turn 1 and change these chunks so that it shows those specific things: Canada, Oceania, and life expectancy greater than 82. So go ahead and do that, and I will start the timer here. Okay, we'll actually stop now instead of 3 minutes from now, because this is hopefully fairly straightforward. All you're really doing is changing like a couple things here. So if you want the data for Canada, we say country equals Canada, and if we run that, there's just Canada. For Oceania, it might be tempting to come here and say Oceania and run it, and nothing appears. That's because we're saying choose all of the rows where country is equal to Oceania. We don't want country. So if we come to Gapminder, we want the continent column. So we can change this to continent. Let's spell it correctly. Continent equals Oceania. There it is. And then life expectancy greater than 82. We need to make sure that we use life expectancy, how it is spelled here. So life, capital E, XP. So we want life EXP is greater than 82. And we'll get rid of the New Zealand thing here and run it. And there's the only two rows where life expectancy is greater than 82. It's Hong Kong and Japan. Great. So that's basically how you filter. Neat. So those are the three answers there. You can actually filter with multiple tests. So this right here would show Denmark after 2000, which would just be those two rows, 2002 and 2007. If you're familiar with these things called Boolean operators, where you can have and or, so like right here, this would be Denmark and years greater than 2000. If I did or, then it would give all the rows where it's Denmark, and it would give all the rows where the year is greater than 2000, which would be all of Denmark plus the whole world after 2000, which might not be what we want there. So that is basically how you filter here. Let's skip up ahead a little bit, just because filtering is fairly easy. So the neat thing about all of these verbs, so filtering, we have the syntax here where we said filter, name of the data, and then the tests. Every dplyr function, like select and mutate and group and arrange and all of those other things, follows that same pattern, where you have a verb, you have a data set, and you have something that you do with that verb. So mutate will add a new column. So if we say mutate the data, and then we're going to do stuff with it. So what this looks like, if we mutate Gapminder and make a new column called GDP that multiplies GDP per capita times population, it will create a new column called GDP. You can do multiple columns. And so this will take the population and divide it by 1 million. And so now we have a column called GDP and a column called, so 8 million people lived in Afghanistan in 1952, 12 million people lived there in 1967. So that's basically the same pattern we've been doing here, is data mutate, data set, stuff you're doing to mutate. So where this gets confusing though, what if you're trying to do multiple verbs at the same time? You want to filter so that you only get the year 2002, and you want to make a column for logged GDP per capita. There's a couple different ways of doing this. One is to make some intermediate variables. So you can filter it and make a smaller data set that is just 2002, and then make another data set that adds this log GDP per capita to that smaller 2002 data set. And so that works. And it's sequential, it's clear. You're saying make this smaller data set, then take that smaller data set, add a column to it. And so you're left with this guy at the end, and that's the thing you want to plot with and work with. So that's one way to do it. Another way is to nest these functions inside each other. So running this will work. So you're saying filter this mutated version of Gapminder and only look at 2002. So this is actually a typo. That should not have 2002 there. So really, like you're saying, take the Gapminder data set, add a new column to it, and then filter it. But the tricky part about that is that gets really ugly. If you have like 5 different things you're doing, like you're filtering and then mutating and then arranging it and then adding another column and then filtering again, you're going to have like a super gross nested list of stuff, and that's awful and miserable. You don't want to do that. So the best solution that comes in this dplyr package is this weird sequence of characters here. It's called a pipe. It doesn't look like a pipe. It's just the percent greater than percent. But that's just what it's called. And what it does is it takes whatever comes on the left of the pipe and passes it as the first argument to the next, to the thing that comes on the right of it, which sounds weird when you say it in words. But if you look at it this way, we've been using this filter gapminder country is Canada. This is the same thing, but written with a pipe, where you take gapminder and you're passing it invisibly as the first argument here in filter. And so that does the same thing. So with multiple verbs, this is what it would look like with pipes. You're taking gapminder and then filtering it so it's only 2002, and then adding a new column for log GDP per capita. Notice what I said when I read this code out loud. I said, take gapminder and then. So that's the easiest way to conceptualize this pipe idea, is think about it as and then. So take gapminder and then filter it and then mutate it. So here's another way of thinking about it. This is the most logical way I've found to think about it. You can have a nested function here. None of this is our code. This is just conceptual stuff. Like you start off with me, and you're going to wake up at a specific time, and then you're going to take the woken up version of me and get out of bed, and then you're going to take the gotten out of bed version of me and get dressed, and then take the dressed version of me and leave the house, with a whole bunch of different options. This is really hard to read because it's all nested and gross. If you rewrite this with pipes, it looks like this, where you take me and then wake up at 8 and then get out of bed on the right side and then get dressed with these things and then leave the house with those things, or using a car, not a bike. So these are identical chunks of code. It's just the pipe, it makes it easy to chain these functions together. So it's really just taking me and then waking it up, and then this, and then that, and then that. Okay, so that is the idea of a pipe in R. So dplyr, again, has a whole bunch of different verbs. We just looked at filter and mutate. You can do all these other things. We won't worry about those right now. So the reason we did this overview here, so now you know how to use RStudio. You can make plots with ggplot, and you can filter things, and you can use that pipe symbol, is because that is the foundation you need to work with the GIS packages in R in order to make maps, because you're going to be using ggplot to make maps, and you'll need to use filter to get rid of different parts of the maps. Like if you have a world map and you don't want Antarctica, for example, you have to filter that out. And the easiest way to do that is with the filter function. So with that, we are now set to do GIS stuff, which should be fun. So let's briefly look at these slides here, and then we will start running some code. So the way you do GIS stuff with R is with this package called SF. And the reason you have to use this SF package is because geographic data is different from all other data. So far, we've been using just regular spreadsheet type things where you have, it's basically like an Excel file that has rows and columns, and that works. You work with that kind of data all the time. Geographic information is stored in files that are called shape files, which are slightly different than the regular CSV files that you've been working with. Because they have to show a lot more information. They have to include information about the projection. They have to include information about borders of different shapes, a whole bunch of other things. When you download a shape file from the internet, it is not a single file. It is actually generally a zip file that has like 5 or 6 or 7 different subfiles inside it. Sometimes they'll come with like a README file. It has a specific smaller file that explains the projection of that data set, if it's Mercator or Albers or any of those other projections we looked at. The shapes, other data. It's confusing because like all of these files are necessary. You can't really just delete them and only work with one. You need all of them. But it's really hard to remember which thing does what. And so the nice thing about the SF package is it deals with all of that for you. So if you, for instance, this is a shapefile of all of the world, basically all the countries in the world. If we use this read SF function and make a data set called world shapes, it will look kind of like a data set. Like here's these columns, there's a type and a geographic unit, and there's actually this data set has like 93 different columns. It's huge. But there's this magical column at the end called geometry. And if you look at it, it looks completely different from regular data. That's because this is the geographic data itself. This is this WGS 84 projection. This is what Google Maps uses. This is the standard -180 to 180 degrees latitude longitude system. And so if you look at this, Fiji, for instance, each of these are points that basically make the borders of Fiji. And it's a really long string of points because it's basically saying draw a line from here to here to here to here to here and make the shoreline of Fiji. So that is kind of the magical part of shapefiles, is if you load the shapefile, it will load all of the other magical files that need to happen, and it will give you a column at the end of your data set called geometry that contains all of that GIS information in a single cell or a single column there. Where do you find these things? The internet. There's a website called Natural Earth that has all sorts of world maps. The Census Bureau has a ton of maps for the United States, county level maps, precinct level maps, zip code level maps, tribal maps, all sorts of things. If you click on that link, or if you use the workshop website, it'll take you to a whole bunch of different places at the census to download shapefiles. For anything else, you Google it. Nowadays, most cities and states and counties are supposed to provide shapefiles for their jurisdictions. And so you can download like a shapefile for Atlanta or a shapefile for Gwinnett County or Fulton County. The Department of Education has shapefiles for all of the schools in the state. Basically, agencies are supposed to do that. The quality of the shapefiles and the systems for downloading them vary wildly by state and by agency. Georgia's system, if you look at the workshop website, it has a link to there. You have to like create a special account and it expires after like a year, and it's a miserable, clunky system. Other states like Utah and Nevada and California just have an open system. You don't have to make an account. You can just download GIS data automatically, and it's great. Georgia's system is like the clunkiest I found. So if any of you know people with GIS stuff at the state government, make them fix it because it's miserable to use. You'll often see when you download shapefiles different scales. It'll say something like 1 to 10 million, 1 to 50 million, 1 to 110 million. These all just deal with how detailed the shapefiles are. So like right here, this 1 to 10 million, that's going to be super high resolution where you can see like borders of specific zip codes. The bigger the number you get here, the less high resolution it is and the more globby it's going to look, which is fine. You might be tempted to just always get the highest resolution of any type of map, which neat, but that's going to make it so that your maps are super huge and complicated. Like if you're just doing a world map for a report, you don't need the highest resolution data ever to get every single like bay in Fiji. It can be more blobby because Fiji is going to show up like this big on the map. So that works. So the way this works, and the reason why we talked about ggplot and stuff here, is because there's a special geom that comes with the SF package called geom SF, and it will automatically plot whatever is in that geometry column, that magic column that appears when you load a shapefile into R. So to get this world map right here, all I have to do is say ggplot, geom SF, and plot this world shapes data, and there's the world map instantly. It's really ugly. You can add other ggplot layers to it to make it fancier, but that's basically how you make the map, which is like incredible. There are other functions where you can change the projections, for instance. Here's the Mercator projection. All we had to do was say, use Mercator. We could switch this to a better one like Robinson. The only thing we have to change is say, use the Robinson projection, which is neat. Every other ggplot thing works with these maps. So if we want we can fill here by population. So China and India are bright blue here, everything else isn't. We can change the labels, we can change the theme. Notice how the grid lines are gone because we use this thing called theme void, which gets rid of all of the theme elements. So everything just kind of works, just like regular ggplot, just with maps. If you don't have a geometry column, there are lots of data sets that might come with a column for longitude and latitude. If you try to plot this with geom_sf, it's not going to work because that's not geographic data. Those are just numbers. R has no way of knowing that this is actually map stuff. But the SF package comes with this function called st_as_sf that will convert those two columns into that magic geometry column, and then it will plot just fine. What if you don't have a column with longitude and latitude exactly? The way I found these numbers is if you go to Google Maps, for instance, this is a fun trick you might not know. If you go to Google Maps and right click anywhere on the map, for instance, right here, after it loads, it's thinking. Okay, so if I right click on the map, it gives you the coordinates in latitude and longitude right there. And so I could like go look up something, write down those coordinates, copy paste it into Excel or something, and now I have a column for latitude and longitude. If you're trying to map out all of your offices for your department, this is probably the easiest way. If you only have like 5 offices, just go right click and figure out the latitude and longitude. If you're trying to map out every single school and you just have their addresses, that's going to be like thousands of schools to map, and you don't want to just right click on Google Maps over and over and over again. That's miserable. But there's a way in R to actually automatically geocode addresses. So if you have a list of addresses like this, you can actually feed it to this function called geocode, and it will use the internet and automatically transform it into GIS data, which you can then plot, which is like super magical. And we'll run examples of all of this in just a minute here. So basically, any GIS stuff you want to do in R, this SF package for simple features, again, that's a special geography term, is all you really need to do. You can draw maps with it, you can calculate distances between points, you can count the observations in a given area, or if you want to find the addresses that are closest to specific schools. Remember that Voronoi map that I showed of like the most popular the most popular basketball teams for specific regions or the closest points to state capitals? Those were kind of goofy examples, but you can do the same thing for school districts. You can say, here's some random house, where's the closest school for it? And that's basically a Voronoi map showing like which school district it should be in according to the rules of geography rather than like political gerrymandering or whatever. So basically anything geography related you can do with SF. There are entire textbooks that are free for how to do this stuff. It's all linked at this website here. If you come down to other resources, I've provided a bunch of different blog posts and tutorials and textbooks that you can use that have all sorts of documentation for how to do this stuff. I'd recommend checking those out and just playing with it. You'll often on the internet, this SF package is only like 4 years old. So if you search for like makeup map in ggplot, you'll find some older tutorials that will say like use this thing called geom map or a package called ggmap. That works, but it's older and it's not the best way to do it anymore because they don't use that geometry column that we'll see in a minute. And so it's really hard to change projections. It's really hard to do other GIS related stuff. So if you just stick with this SF package, it will make life way easy for you. And so let's do some stuff with it. So if you open up the 4th R Markdown file in RStudio, we'll do some basic GIS plotting. So if you notice, this first chunk is actually longer than what you've seen before. And that's mostly because I commented all of this stuff pretty extensively to help future me remember where this stuff came from. So we're loading tidyverse, we're loading this SF package, which we need to do. But then if you notice here, like within a chunk, anytime you have this pound sign, that means it's a comment. It's not actually going to run. So you can type whatever you want. This data often shapefiles are like deeply embedded in websites. You have to click on a whole bunch of different links to be able to download them, and it's miserable. And so what I will often do is say, like, I will write out instructions for where to find these things on the websites, and then I'll unzip them and put them in the project here. So this first one will load a shapefile called world map based on this really long file name that I got from Natural Earth. So if you go ahead and just click on the play button for that first chunk, it will load all of those shape files. And let me show you what this magical geometry column is. So if you scroll down, let's look at US states. If I click on US states here, it shows that there's 52 rows and 10 columns. So if you look here, there are regular columns in here. The neat thing about shapefiles is they're just regular data sets. People can include whatever columns they want in them. It doesn't have to just be like coordinates for geography stuff. So here we have like the state name, the state abbreviation. We have these FIPS codes, which is the Federal Identification System for states and counties. So this lets you actually merge other data into the shapefile. So if you have state level data based on FIPS codes, you can actually bring that into this data set and then plot it. If you scroll all the way to the edge though, you have this column called geometry, and that's the magic column. If that is in there, you can then plot stuff automatically. Like you don't have to worry about converting these points to different coordinate systems or projections. It will just happen for you. The geometry column is just there, which is great. So that's what a shapefile looks like in R. Regular data set, very end, you have geometry. If you add a new column using mutate, it will actually stick it before this geometry column. Like the geometry column will always be the last one, just because that's how it is. If we click on world map, for instance, this one has like 100, it has 95 different variables, and it's a ton. So that's because if you scroll through, it's got like country names, country abbreviations, and it's got country names in different languages. If you keep going over, the formal name, like the Republic of Fiji, regular Fiji, they included population, they included a whole bunch of other things in here. You don't actually see the geometry column because RStudio only shows you 50 columns at a time. So if you click on this little arrow here, it will show the next page of columns. And so you can keep scrolling through, and now we'll start getting different languages. Like they'll have Arabic and Bengali and German, neat. So if we keep going, there's the geometry column. That's what we need, and it will plot stuff. So if we come back to the fourth R Markdown file, scroll down to this world map section. So notice this first chunk of code here. We're going to make a new data set called World Sans Antarctica to be able to get rid of Antarctica. So we're going to take that world map data set. Notice this pipe. So that we read that as and then. So we're going to take world map and then filter it so that the ISO column, which is the abbreviation column, is not equal. So that's the not equal to ATA, which is the abbreviation for Antarctica. And the only way I found that was by looking at world map. I actually filtered it based on the name and found Antarctica, and then I found the ISO code for Antarctica right there. So that's how I did it. So if I run this chunk now, I have a new data set called World Sans Antarctica, and it only has 176 rows instead of 177 rows because one row disappeared, Antarctica. So now to plot it, we just hit play. And there is our world without Antarctica. It's a really ugly map, but it's there. We didn't have to set any aesthetics. Notice how we didn't say like X equals latitude, Y equals longitude. That's because this geom SF handles the X and Y for you automatically, which is nice. You can add other aesthetics though. So we have this your turn here. I'm going to do it for us for the sake of time here. So I'm going to insert a new chunk. What we're going to do is take the same ggplot SF stuff. I'm going to put it right here. So what we can do is we can say fill equals red, for instance. Let's see what that looks like. Yeah, super ugly. We can say color equals white. That should do the borders. Yeah. We can do size equals 0.5. That should make the borders thinner. Or 0.25 will make them extra thin. So let's run it again. Yeah, so it's starting to improve because we don't have thick, chunky borders there anymore. So basically all of those things that we saw before, I'm not mapping any of the columns to fill and size and color. I'm just telling them to be a specific fill, size, and color. But that helps kind of improve this map here. But you can take columns in the data set and transfer those to parts of the map. So if you scroll down to this next chunk here, what we're doing is instead of saying fill equals red, the nice thing about that natural earth data set is it comes with columns that make it so, like if you ever look at a map, they choose specific color locations so that no two countries ever share the same color, which is how like fancy cartographers figure that out. And the data set comes with columns that like have a 9 color scheme and a 7 color scheme, which is nice and convenient. I'm glad they stuck that in there. So what we can do is take the 7 color scheme, for instance, and fill all of the countries based on that 7 color scheme. And I have a couple other layers here just to make it a little bit nicer, like a nicer color palette, to get rid of the legend and to get rid of all of the grid lines. So if you click on play here, you should get something that looks like that. We now have a fancy world map. You could print that out and share it with your friends, and that's great. So that's mapping. It's really just using basic ggplot functions and adding them to geom_sf here. Changing projections is super easy. You just use this coord sf function and tell it to use a specific projection. So this cryptic code here for Robinson, for the Robinson projection, which is my favorite for the world, I only know this because I used that EPSG website. So if I select this URL, I'll show you what that website looks like here. Okay, so what I did is I searched here at the EPSG website for Robinson World, and it gave me this, and then that is the secret code that I have to use to make it use Robinson. So I just copied that, this ESRI:54030, stuck it here, ESRI:54030, and now if I run it, there's the Robinson projection. Okay, so what we can do is the same thing. I'm just going to copy this chunk, including the triple backticks. And if I come down here where it says insert chunks here, we can change it to different projections, like the Mercator projection or the sinusoidal projection. So what I want you to do is in the next couple minutes, copy this Robinson code that I gave you, paste it down here, and then look at the workshop website. I actually have a list of different projections right here that are common, like Mercator and sinusoidal and Malweed, I guess, and just change the projection to some of those other ones and see what it looks like. So like Mercator is EPSG 3395. So if I come here and say EPSG 3395 and run it, yeah, there's ugly Mercator. Look how big Greenland is. That's ridiculous. So go ahead and take a couple minutes and play around with these different projections and run the chunk and see what they look like. And just experiment with that for about 90 seconds. Okay, cool. So hopefully you saw some fun ones like the sinusoidal or the mall-wide, or I think one wacko looking one is this ESRI:54002, the equidistant one. This one should be, yeah, super stretched out and weird looking. Great. So yeah, like all you're doing is just magically adding a whole bunch of different or changing different coordinates. The really cool thing is you can actually layer a whole bunch of different geom or SF layers from different shapefiles. And even if those shapefiles inherently have a different projection, like this world one that loaded, I think is Mercator, it's the negative 180 to 180. If I'm then going to layer a different projection on there, this chord SF makes it so all of the geom SF layers follow the same coordinate system. So you don't need to worry about shapefiles being in specific projections. This just forces them all to fit nicely together, which is really cool and saves a ton of time and worrying about what projection is what. Same thing works for maps or for US maps. So if we take, instead of using that world map data set, we can use the US states data set. This came from the census. What we can do here is we're going to filter it so that we're going to get rid of Alaska, Hawaii, and Puerto Rico just for now. So we'll only plot the lower 48. So if I run this, we should have a smaller data set now called lower 48, 49 because DC is in there. And then it follows the same syntax. We have geom SF. We're going to plot that lower 48 data set. We're going to fill with dark red. We're going to have white borders, and we're going to have thin white borders, this 0.25. These color names, R has a bunch of built-in color names like red and yellow and dark red. You can Google lists of R color names. What I generally do actually is not that. You can also insert hex colors if you're familiar with HTML. So if you go to Google and search for color picker, it will give you a fancy color picker here. And you can drag this thing around and choose your own color. Like, let's do this red. That's a neat color. It'll give you this hex code right here, this DB2577. If I copy this hex code with the pound sign, and instead of saying dark red, I can use the hex code, it will use that color. So if I plot this, there's that same pinkish color there. Okay, so there's our US map. We're using this projection, which is this NAD 83. That's the Google Maps system, the negative 180 to 180. If we want it to be Albers instead, we just have to find the Albers projection number, which I have conveniently given you at the workshop website. So if you scroll down to Albers is ESRI 10 2003. See if I can remember that. ESRI 10 2003. It worked. There's Albers. So there's the nice curvy northern border there. And there's the Albers United States. All we had to do was change the projection from that NAD 83 to Albers, and it magically happened, which is really cool. But we've gotten rid of Alaska, we've gotten rid of Hawaii, we've gotten rid of Puerto Rico, other things. It's just the 48 states. We can add those. There's a package called Tigris right here that actually lets you connect directly with the census. And so you can download shapefiles directly from R. I haven't ever used that. I just download the shapefiles on my own, but there is a way to get it directly from R without having to go look at the census website. But the really cool thing about Tigris is it comes with a function called shift geometry, where what it does is it takes that magical geometry column, and if it notices that Alaska, Hawaii, and Puerto Rico are in that geometry area, it will rewrite that geographic data so that it places Alaska where Mexico is, and it places Hawaii where Mexico is, and it places Puerto Rico in the middle of the Gulf of Mexico. And so it actually rearranges like those points and puts them in other places on the map. And that works for anything. If you have a data set of all of the schools in Alaska, and then you feed that data set to shift geometry, it will go through and change all of those schools in Alaska to be in the middle of Mexico so that they show up in a map underneath the United States. So for instance, if we run this here, we're gonna shift Alaska, Hawaii, and Puerto Rico using shift geometry. and then we'll plot it using Albers. So if I run this, you can see what I mean by putting it in Mexico. So there's Hawaii right there, there's Alaska right there, there's Puerto Rico. Again, if we had a separate data set of all of the schools in Alaska, those would all get plotted as points down here, because it actually rewrites the geometry information to show up on the map here, which is really cool. There's other options. If you you can have Alaska show up here by Seattle, have Hawaii show up on the side by California, and have Puerto Rico be over here. To do that, I think you say, yeah, so in shift geometry, you can say position equals outside. See if that is correct. Yep. So that'll put these states on the outside of kind of where they are. So Alaska's up there, Hawaii's down there, Puerto Rico's there. By default, it does inside, but you have to spell it with an E, not a 3. It's not that, it's called below. Below. So you can actually look at the help page for shift geometry. If you go to the help panel and then search for shift geometry, it should then show all of the different options. Oh, it's here, shift geometry. Yeah, so then this explains how to use shift geometry, position would be below, outside, etc. So yeah, you can do that. Using the same filtering idea, we can take that 48 state data set and only pull out the Georgia row. So if we do that and then plot the only Georgia data set, there's Georgia. We got a Georgia map just with like 3 lines of code. It's amazing. If you notice though, this is where the resolution starts mattering. If you look down at the coast, you can't see any of the islands because this is kind of a lower resolution version of Georgia. So one of the shape files that I had you load at the very beginning is this US states high resolution data, which is more detailed. So if we come back down to our Georgia chunk, rather than extracting Georgia from this lower 48 data set, which is the lower resolution one, we can extract Georgia from the high resolution data set. Notice how the filtering here is a little bit different. Here I said filter it so that name is equal to Georgia. The only reason I did that is because in this US states data set, the column with the names, or with the state names, is called, so US states. The column with the state names here is just called name. As I said, name equals Georgia or Ohio or whatever. The high resolution data is a little bit different. If we look at it, high res, it has columns. This is actually like all provinces in the whole world. So here's like a region in Pakistan, and here's Gujarat province in India. And so I had to basically like sort this column, find US, and figure out the US states, so if you scroll down here, we're taking US-GA, that's going to be Georgia in that data set. So we're going to filter it. And now if we plot it, much nicer. You can actually see the barrier islands here and more detailed borders because it's higher resolution, which is great. So that's basically how you do kind of standard GIS plotting. You load a shapefile, you filter it if you need to take out any rows you don't want to plot, and then you use geom_sf to plot that. You can fill it with specific colors. You can fill it using one of the columns in the data set, like a population column. You can fill it by region, a whole bunch of other things. It just magically knows. So far, we've only been plotting like regions, like borders. If you have a shapefile that is, for instance, all of the public schools in Georgia, that geometry column is going to not be a whole list of numbers. It's just going to be 2 points. It's going to be a latitude and longitude point. And if you use geom_sf with that data set, it is smart enough to know that those are points and not a blob of borders. And it will put points on there too. And you'll see that in just a minute when we switch to number 5. So go ahead and switch to the 5th R Markdown file here for multiple layers. And run this first chunk. So we'll load a whole bunch of shape files again. Okay. So scroll down to about line 56, the first chunk that you see after the shape files. We're going to once again use filter to extract some stuff from the shape files here. So one of the shape files we loaded was US counties. So we had been working with US states, but now we have a data set called US counties, which I got from the census again. So if we scroll down and let's look at it, here's our county data set. There are 3,233 counties in this data set. We have a whole bunch of stuff in here already. State FIPS codes, county FIPS codes. I don't know what that is. I don't know what that is. I don't know what that is. There's the name of the county and a whole bunch of other columns. I think this is the area, the land area, the area of the water in the county. The census included that information for us already. Neat. And then the very last column here again is the magic geometry column that has all of the geographic information in it. So we want to just get the counties that are in Georgia. So the column here for state is called, where is it? Scroll down to, okay, is state FP. So the state FIPS code that the government uses for Georgia is 13. Only way I found that was actually just like scrolling through here. Instead of Googling it, I just searched for Gwinnett County because that's where I live, and there's one in Georgia, and I figured out that the state FIPS code was 13. There are probably better ways of figuring that out, like actually looking up a table of FIPS codes, but that's what I did. So if I run this chunk, now we should have a data set called Georgia counties with 159 counties in it. Scroll through, there's Forsyth County, there's Grady County, there's Lanier, etc. Everything's in there. Neat. So to plot this county data set, it's going to be the same thing that we've done before. We're going to use geom_sf to plot counties. And it's going to be ugly, but there's all the counties in Georgia. Neat. So what we could do, though, is we can start layering things. So if you look at this next chunk, what we're going to do is plot the Georgia state by itself and then add the counties on top of it. So to show you sequentially what's happening here, I'm just going to select from the beginning of ggplot to the next line right before the plus sign. And if I then press Command Enter or Control Enter on Windows, it will only run those 2 lines of code. And make sure you don't get the plus sign, otherwise it's going to want to keep running code after that. So if we just do this, this should just be the state. And I gave it a big, thick purple border around the state because I did. But then, so that's one layer. If I then select up to the next layer, and we'll add the counties on top of it, what this lets us do is give a purple border around the state and then have the counties all be green with kind of a white border between all of the counties. The only way to get that purple border on the outside is to have those multiple layers there. Had I said to use color equals purple for the counties, then every county would have a purple border around it. And so because we layered it, we have the state layer underneath with one type of border, and then we have the counties on top with a different type of border and a different type of fill, which is cool because we're just taking those 2 different data sets and plotting them at the same time. We can then use filter to only show some of the counties. So we can extract just the Atlanta area. So that's what's happening here. We're saying filter the name of the counties and only include these counties: Cherokee, Clayton, Cobb, DeKalb, etc. And that will give us a smaller data set. How many rows? That gives us 10 rows in here. So there's our 10 Atlanta counties. If you look at the code here, we're taking the Georgia state boundaries, and then we're going to put the Atlanta counties on top of it. So if we run that, there's purple Georgia with green Atlanta right there, which is pretty cool. All we had to do there was just filter the shapefile data set and then plot a couple different data sets all at the same time. We're layering it all on top of each other and it just works, which is amazing. Okay, so we're going to skip the your turn thing. We're going to look at a couple other things. So we also, just for fun, I loaded, we'll skip this one for the interest of time too. I'll walk through it really quickly. So one of the data sets that I gave you is called rivers_NA for North American rivers. So these are all the rivers in North America. If I want to plot all the rivers in Georgia, if I click on play right here, in theory, it should do that because we're going to plot Georgia and then we're going to put the rivers on top of it. But if you look at what happens, that's what happens. There's Georgia right there, but then it plotted every single river in all of North America, which is not helpful. We didn't want that. But we can use some specific functions in the SF package to basically use a cookie cutter and take the shape of Georgia and slice down this river data so that it only includes the rivers that cross the border of Georgia. And then we can plot that. So the code for that is down here below. It's this ST intersection. So we're feeding it two different data sets. We're saying take Georgia, use that as the first one. That's going to be the cookie cutter. And then basically slice it through that rivers shapefile so it only includes the rivers inside Georgia. So that's what ST intersection does. If you look at the actual documentation here, I had to do a couple things, mostly because the Georgia shape uses a different projection than the rivers shape. And so I had to transform one of them to match so that I could then use the cookie cutter correctly. But once you do that, this is what you're left with. You have a data set called only Georgia, and you have a data set called the rivers just in Georgia. And so that's the cookie cutter version. It just sliced everything off. So if you're doing something, for instance, trying to find all of the students that are in specific school districts, that's what you do. You use ST intersection to basically do a cookie cutter through all of the students and only select the ones that are inside those regions. And now we have a map of Georgia with all of those things there, which is great. So if you scroll down to the plotting schools in Georgia, we'll show you that section next. This shapefile, if you look at the Georgia schools shapefile, this I got from the Georgia Department of Education's GIS system, or it was the state system. It's whatever awful system Georgia has for getting GIS data. This is from 2009. That was the most recent data. This is every school in Georgia in 2009. It has a whole bunch of columns for like where the county of the school, the district of the school, the name of the school, the grades it includes. That's neat. There's the address, cities, state, zip. If you scroll all the way to the edge, there's the magic geometry column. Notice how it's a little bit different than before. It's only giving 2 points here, rather than a whole bunch of points that we were seeing before where it was giving like borders. This is just a single point. Also notice that the geometry here is weird. If we look back at like Atlanta counties, these coordinates are the -180 to 180 system. So like -84, -84, they're basically all -84 because it's around Atlanta. This one though uses like 2052182, like that's almost in the millions. And that's the coordinate system it uses. I don't know what coordinate system that is. It might be Albers. Albers actually measures its coordinates in meters away from the equator. So it might be meters there. Those are huge numbers. It ultimately doesn't matter because we can convert this geometry column to whatever we want. And we don't really need to care what it is when we're plotting it because that chord SF layer just forces it to be whatever we want it to be. So you can kind of ignore whatever system it's using right now because it doesn't really matter. So if we want to plot those, we're going to use the same system. We're going to use ggplot and then plot the Georgia schools layer. So if you click on the green button here, you'll get a bunch of points, except this often happens with real data. There's Georgia up here, and then there's 1 point off by itself in the middle of the ocean. Whoever made this data incorrectly typed the coordinates there. And I think I looked up where that is. That is, it's in Indonesia. That's where that one point is. So we can actually see it, like what I had to do. You can actually tell that there's an error here. I think I sorted by like the congressional district column. And then if you go to the very end, it shows you that that is actually missing. So whatever row this is missing the congressional information, Senate, House seats. And if you look at the geometry, it's actually completely different. All of these others are like 226, 227, and for whatever reason, this one's like 539. So if you scroll over, you can see what school that is. That is Alatoona High School in Cobb County. It is miscoded in the data set. We could go and like Google it and figure out the coordinates and fix it, or for the sake of this, we'll just get rid of it. And so that's the ID for it. So we can filter that data set to get rid of Alatoona High School based on that ID. So that's what happens here. Georgia schools fixed. We're going to take that Georgia schools data set, filter it so that only include, or it doesn't include 22097, and then we'll plot that fixed data set, which looks like that. So those are all of the schools in Georgia, which kind of makes the shape of Georgia, because it does. It's also basically the population density of Georgia. But if we want to put this on a map of like a state map, or maybe show county borders, we just do the layering system. So we take the Georgia state map, plot that first, and then put the points on top of that, which is what happens in the next chunk. So we're going to take the high resolution Georgia data, plot that, and then put the schools on top of it. So if we run this chunk, there we go. There's a map of Georgia and all of the schools. That is kind of ugly. Like there are a lot, like Atlanta's just a big black hole right here because the points are big. So we can shrink the points down a little bit and make them partially transparent, so that if you have more points on top of each other, the area will get darker. And if you only have like one school, it'll be a lot lighter. So if we run this chunk, we're just shrinking down the points and making them transparent. That looks a lot nicer. It worked. Rather than specifying exact colors, like right now it's just black, we can map any of the columns in this data set to the color. So we, for instance, could color by congressional district. We could have each of the points be colored by the Senate district or the House district or the congressional district or whatever. I think it includes a column here called total. I think that is the size of like the number of students in the school, is my guess. There wasn't a lot of documentation for this data set, so I'm just hoping that that is the number of students in the school. Makes sense, like 500 students, that's a reasonable amount. Let's sort it. There's a school with one person in it. That's Effingham County Gateway to College Academy in Effingham County. There's one student that goes there. I guess that's true. If we sort total by the other direction, we see there's 4,000 students in a school, Mill Creek High School in Gwinnett County. Actually, all of these Gwinnett County schools, Peachtree Ridge, Grayson High, Brookwood, they all have like 4,000, 3,000 students in them. That's wild. Gwinnett's just different, I guess. We have Gwinnett County people on the call here. You probably know why. I don't know why. They just have really big schools in Gwinnett County. We can actually visualize that. So instead of saying have the color be black, we can use this AES function to make that total column, get mapped onto the color aesthetic. So all of the points will be colored by the number of students that are in that school. So if we run this chunk, there we go. So most schools are down here in this dark blue, blackish range here, except you can see this cluster of green and yellow. There's Gwinnett County, where for some reason we have like 4,000 students per high school here in Gwinnett County. But you can actually see that on the map. And again, that takes very minimal code. We're just taking the Georgia data set, taking the Georgia schools data set, plotting it, and adding a couple things to make it a little bit nicer with a better color scheme and getting rid of the grid lines. And now we have a map. All right, so really briefly, let's look at the sixth option here for geocoding. Because right now, all of the stuff I've shown you has assumed that you have access to shape files, which you do, they're all public. You can download stuff from the Georgia system, from the Atlanta system, from the census, from that Natural Earth website. You can get all of those shape files from there, but often you have data sets that don't have shape files in them. You might have columns for latitude and longitude. You might just have addresses. And if you want to be able to plot those, you need to get that magic geometry column. Otherwise, it's not going to plot. So to do that, we can do it in a couple different ways. Go ahead and load this chunk that will load a whole bunch of shape files again. It's mostly the same ones we've been working with, but they're all in one place here. And it loads this package called tidygeocoder, which we'll use in a minute to convert addresses into geographic information. So if you scroll down to this very first chunk, what I do here is I create a miniature data set that's just 3 rows and 3 columns called Georgia cities. I got these coordinates from Google Maps just I went to Atlanta, right-clicked somewhere in downtown Atlanta and chose those coordinates. I think I actually right-clicked on the Andrew Young School in downtown Atlanta. With Athens, I don't remember what I clicked on. That might be the library at UGA. Savannah, I just clicked on something. So you might have a data set that looks like this in Excel that has a latitude column and a longitude column. We cannot plot this right now because R doesn't know that those are geographic things. It just thinks that those are numbers because it's just numbers. So what we can do is use this function called st as sf. ST, I don't know what it stands for, something. SF means simple features. So what it's really doing is converting numbers into simple feature data, or that magic geometry column. And so what you have to do is tell it, so we're going to take that Georgia cities data set, and then, so there's the pipe, we're going to feed it to st as sf. The coordinates we want it to look at are long and lat. That just aligns with whatever's in the data set. So if this was named latitude and longitude, then I'd have to type down here longitude and latitude. Like whatever it is here, it has to match here. And then I have to tell it what coordinate reference system or projection it's currently using. So this system right here, Google Maps, uses basically Mercator. It's a special system, the GPS system, which is this EPSG 4326. I discovered that by Googling. And now you don't have to discover it because I discovered it by Googling. So it's here. So this projection right here, this negative 180 to 180, is this EPSG 4326 thing. So what we're doing is we're saying there is information in this longitude and latitude column that is currently as this GPS EPSG 4326 thing, convert that into a geometry column. So if I click on play here, it did it. So here's our city column with Atlanta, Athens, and Savannah. And now, instead of having latitude and longitude, those columns disappeared and got converted into our magic geometry column. If we look at it over here, I called it Georgia cities. If we open it in this tab here, you can see the same thing. There's our numbers that we had before, but now it's this fancy geometry thing instead of latitude and longitude, which means we can now just plot it with geom_sf. So we'll layer it just like we've been doing before. We'll add one layer with the state boundaries, and then we'll add a layer with the cities. And if we hit play, there's the 3 cities. And it knows how to do that because it just does. If we wanted to change the coordinate reference system or the projection, it would automatically convert the boundaries and it would convert those points because it is, again, that cool geometry column that contains all of the GIS information. If we want to add labels here so that we know that that's Atlanta, Athens, and Savannah, there's a cool function called geom_sf label. which if you tell it what column to set as the label, so we'll use that same mapping system. We'll say, take that city column that we have, because that's the name here. We have a column called city, and have that be the label. If we plot this now, we'll get the points, we'll get the state boundaries, we'll get the points, and we'll get the labels, which is really, really tiny on here. It probably won't be that small on your computer. But we can actually control the size here. If I say size equals 10, see what that does. It got a little bit bigger. Size equals 30. See what that does. That's probably too big, but it worked. Okay, so that lets you do points and the labels and the state boundaries all at once. And the neat thing is we didn't have to download any shapefile for that. We didn't have to go find some data set of city coordinates. We just made our own little data set and then used this st as sf to convert that latitude and longitude into geographic data, which is great. But what if you have just addresses? So scroll way down to this chunk at like line 116-ish. I made a tiny little data set called some addresses, which is 2 addresses, the address for the White House and the address for the Andrew Young School. If you look at this data set, it's just those 2 rows. There's no latitude and longitude information. It's just an address. So if we want to map this, we could either select this text, go to Google Maps, search for it, right click on it, get the coordinates, put that in a data set, and then use st as sf to convert it into geographic information and then plot it. That's miserable if you have like 50,000 addresses. So you don't have to do that. If you load the tidygeocoder package, which we did at the beginning, this gives you a magical function called geocode that will take an address, feed it into an online system, and return the coordinates for it. This is like intensive stuff, and there are lots of systems that do this, and they're all a little bit different. Lots of them are paid systems. There are some free systems, like the census lets you do this for free, but it has a limit. I think you can only do like 50 an hour or something. Like they rate limit how many things you can geocode. Google they used to have a free system. They don't anymore. I have a list in this R Markdown file of all of the different systems that this tidygeocoder can connect to. Some are, the first 3 here are free, but with limits. So like ArcGIS has a system that has, I think it lets you do like 100 an hour or something. The US Census has a system. OpenStreetMap has a system. All these others like OpenCage and Mapbox and TomTom, you have to pay for those, and then they give you something called an API key that lets you use their system. So we're not going to do that because that's expensive. So we'll just either use OSM or Census or ArcGIS because those are all free. So if I come down to here, we're going to take that some addresses data set. We're going to feed it into geocode. The column name in this data set is called address, because that's what I called it. Had I named it anything else, I'd have to use that name here. And we're going to see if the census can handle those addresses. In theory, it should, because like it's the census, but we might be blocked or rate limited. Let's see what happens. So run that chunk. It's connecting to the census's server. Let's see if it did anything. It did. It might not, like, so it wasn't always working for me, because sometimes the census server gets overloaded. And so if you don't have a latitude and longitude column, go ahead and switch census to like OSM for OpenStreetMap or to ArcGIS, and either one of those should hopefully work. Hopefully the census one worked for you. But yeah, now we have latitude and longitude automatically determined because of the census's servers. So now if we want to plot those, we do the same thing that we did before with the cities. We have latitude and longitude. We just now need to convert that into that magic geometry column, which we can do with st as sf. So if I run this chunk here, Now we have a data set with a name column, an address column, and our magical geometry column, which means we can now plot it. And so if we plot this next chunk, we're going to take the lower 48 map, have that be underneath, and then put the addresses that we just geocoded onto the map. And there's the White House, and there's the Andrew Young School, just like that. So that is kind of a super brief overview of how to do this stuff. The SF package really makes it easy to do this geographic stuff. Prior to 4 years ago, you had to worry about the projection for every data set that you had in here. You had to constantly convert all of the different data sets to specific projections. And that was always really hard to do. This does it for you. Geocoding is fairly instant. If you're doing like bulk geocoding with like thousands and thousands of rows, you'll have to look at the documentation to see how you can get API keys, and you might have to pay money to do that, or have an intern go right click on Google Maps all day. And the cookie cutter system that one of you mentioned, wanting to like put students in chunks, geographic chunks, you use ST intersection for that. You can calculate distances between things. You can do all sorts of things, all with this SF package. And then actually plotting it is like really, really easy. You just say geom SF, name of the data set, and it's there. And you don't have to worry about projections. You don't have to worry about anything. It's fantastic. And because it's all just based on data sets, all of those cool dplyr things that we talked about with like mutating, arranging, filtering, that all works as well. So it's really easy to take out specific counties, to highlight specific areas, to get rid of entire countries. You can merge in other data from outside sources and plot that. It's fairly flexible and easy to use once you get the hang of it. So I'd recommend just playing with this stuff. You have all of the code here. The workshop website also has a ton of other resources. A similar example to what we just ran here in RStudio.cloud. If you click on the very last link on the workshop website, it says there's a lecture and complete example video and code from my GSU class. So if you click on that, this also explains what shapefiles are and basically goes through everything that we just did. And if you want a video version of that, I have kind of a video tutorial here that you can watch. So everything is there. Have fun with it. The best way to learn this stuff is just to play with it. So play with it. And thanks, everybody.